Hey guys, welcome back. My name is Mr. Kim, and I'm going to go over the August 2024 Regents Chemistry, the free response questions. Well, let's get started. Question 51, draw a Lewis dot diagram for a molecule of ammonia. All right, so how do we get about doing that? Well, you know, as well as I know, you should. Formula of ammonia is NH3, right? So I don't know how to say this, talk about this, but you're just gonna have to know ammonia, right? It's not in a reference table. That's not ammonium, right? It's ammonia, right? That's what they said, right? Um, yep, it's ammonia, right? So, again, there's no good way to say. You just have to know that it's ammonia is NH3, right? So you might want to memorize that. So let's talk about drawing Lewis diagrams, right? We got nitrogen, we got hydrogen, right? Nitrogen, what is it? It's 5 valence electrons, right? I mean, you should know that, but if you don't know that, right? 5 valence electrons. Hydrogen has 1, right? So therefore, nitrogen has 5 valence electrons. Nitrogen has 1, except it's got 3 in ammonia. So that comes out to a total of 8 valence electrons, right? So let's go ahead and draw this. It would be nitrogen here, right? And 3 hydrogens. Maybe draw it like this. Make 3 bonds. Each bond or a dash is 2 electrons. So out of 8, we used up 2 times 3 is 6. You're left with 2 valence electrons. And what do we know? Nitrogen needs an octet. So we're going to put an octet right here. And this is your answer. Next question. It says the table below gives the atomic mass and natural abundance of the 2 naturally occurring isotopes of copper. Compare the energy of electron in first shell of copper, right? First shell in the ground state to the energy of an electron in the second shell, right? So what are we talking about? We're talking about the nucleus of copper, right? And you got first shell versus the second shell, right? So what do we know? Remember, as you go further away out, it is higher energy level, and if you go lower, it's the closer to the nucleus, right? So you would say, let's go back to the question, energy of an electron. So the electron in the first shell will have, do you guys remember? Lower energy, right? Than the electron in the second up shell. Okay, so that's 52. Let's go to 53. It looks like they're going to make us draw something. Show a numerical setup. Oh, I was wrong. Numerical setup for calculating the atomic mass of copper, right? If you are coming to this video after seeing the other video, you realize, oh, they made us do this before, so let's do it again. It's going to be what? The sum of the atomic masses of the isotope times its natural abundance, right, as a decimal, right? So it's going to be 6293, 69.15%. So it's going to be 62.93 units times, what was that again? 69.15%. So that's 0.6915 plus this next isotope is 6493. 64.93 times percentage is 0.3085. And like I said, they're asking you for the numerical setup. They're not asking for the answer. So that's the correct answer. So this is one of those where, like I was saying in class, if you punch this into a calculator and you write down an answer, you just got this question wrong. Okay. So if you put this into a calculator and you wrote the answer without writing this work, you just got it wrong because they're asking for the work. Okay. All right, number 54. The element in the periodic table vary in their properties. The placement or locations of elements in period 2, that's important, so I'm going to underline it, give an indication of the physical and chemical properties of these elements. It says, identify an element in period 2 that is classified as a metalloid, right? What's that? That's the stairs guy, right? So let's go. So when you go here, we're looking at period 2, right? Right here. And we're looking at somebody that's either sitting on or hanging off of the steps, and that would be boron because your metalloid, right? Your metalloids are located along this line right here, right? So the answer for that one would be boron. Okay, let's go to 55. Identify the element in period 2. Once again, we're going across left to right in period 2, right? That requires the least amount of energy to remove the most loosely held electrons from a mole of gaseous atoms of the element in a ground state. Now, what in the world is this, right? Energy to remove all that. This is a definition, isn't it, right? So what is this definition about? Energy to remove the loosely held electrons. This is definition of ionization energy. Okay. Now, I don't know what to tell you. You just have to memorize the definition of ionization energy. So when you see it, you recognize it. And then the other thing you need to remember, right, with periodic trend is that how does ionization energy work? Ionization energy is opposite that of radius, right? So in order to answer this, you also need to know what the radius goes, right? Now you're going left to right on a period, right? Which means in order for us to figure this out in a, how does radius work? Radius is it gets larger, right, as you go down. And then it actually gets larger if you go to the left, all right? So, and I think one of the students actually came in and asked me about this ninth period, right? But if you go, how do you get the largest guys? We get the largest guys going to left. And what do we know? We want the one with the least amount, which means we want the largest radius, right? Remember, it's opposite that of the radius. So therefore, looking for somebody that's, right? We're looking for a chunky guy, right? And what do we know? That means that we want to be, because we are going in terms of a period, going left to right, we're looking for the guy that's the largest. In this case, it would be the leftmost person in period 2, which means going over here in period 2, leftmost element would be lithium. So you would say Li or lithium. Okay. All right, let's go to 56 and see what that question is about. 56, state the general trend in atomic radius as elements in period 2 are considered in order of increasing atomic. Oh, look, we literally answered it right here. But what are we doing? We're going in increasing atomic number, which means what? We're going that away, which means it's large radius to small radius, right? So what's the answer? It's decreasing, right? So the answer is it's good practice to start your answer sentence with the actual answer, right? So what are we looking at? We're looking at the general trend of atomic radius, right? So you'd say atomic radius decreases as we move across the period, right? And in terms of what? In order of increasing atomic radius. Okay? So that's what we would be expected to say on this problem. All right, folks, let's move on to 57. 57. An aqueous solution of lead to nitrate reacts with aqueous solution of potassium iodide in a test tube. The reaction produces a yellow solid that settles to the bottom of the test tube. So it's a yellow solid that settles at bottom of the test tube. So what we're looking at, that's probably this guy, right? Because remember, that's a solid, right? The unbalanced equation for the reaction is shown below, okay? Balance the equation in your answer booklet for this reaction using the smallest whole number coefficients. All right, so let's go. Remember, I told you in class that I think that you should try to graduate away from using the charts. I mean, you can, but let's take a look at this one. We got one lead on the left side, and you got one lead on the right side, so we're okay for lead for now, right? Let's take a look. Let's look at nitrate, right? Instead of breaking this down into nitrogen and oxygens, you have how many nitrates? You got two of them here. So and therefore, I'm thinking I need two of these right here, like that. I have two potassiums, so I'm going to increase it. Oh, sorry. To two potassiums like that, right? Now let's go. Now I have two iodide, and I have two iodide. So it looks like, guys, we're done. Okay? Oh, it's that easy. Okay. All right, 58. Write a chemical name for the aqueous product. Who's the aqueous product? That's this guy, right? Well, how do we name that? Well, you know the first part is potassium. What's the second part? Is it potassium, nitrogen, oxygen? No, that's stupid, right? So what is it? It's KNO3. So if you don't know, I remember I told you it's not a bad idea to memorize this chart, but if not, you're gonna go over here and look at the table E. And what do we know? NO3 is right. Oh, where'd you go? Right here, right? It's nitrate. So it's potassium nitrate, right? So you would write potassium nitrate. Okay. All right. Let's continue going. Determine the gram formula mass of the yellow solid compound. All right. So what? Right now, what I'm going to do is I'm going to change this to that. Because I know that's the yellow solid compound, right? It's solid right here. Then with the gram formula mass, that's not that difficult, is it, right? What is it? It's the sum of the atomic mass numbers, right? So let's do some math over here, right? So we got lead right here. And what is lead? You got to go to your reference table or the periodic table. And over here, lead is right over here, and it's 207.2. So lead is 207.2 grams per mole. And iodine is what, 35.45, I think? Oh, nope. I got that wrong. That's chlorine. That's 126.904. So iodide is 126.904. Except, what do we know, guys? That's right. We need two iodines. Okay, so that's how you do it. And if you put the two together, I believe you should get 461.0 blah, blah, blah. But it is 4 sig figs. So I'm going to put it into the calculator, and the answer should be 461.0 grams per mole. Now, don't worry so much on the sig figs. I think the Regents are a little bit loosey-goosey when it comes to sig figs, so it looks like they're going to accept 461. But like I said, you probably want to try to stick to sig figs as much as possible, because if you don't, you may round yourself out of a correct answer. Okay. All right, let's continue. Base your answers 60 through 62 on the information below and your knowledge of chemistry. Vapor pressure of 4 liquids at various temperatures are given in table H. All right, so let's go to table H. All right, so to go to table H, let's go. That's a table that we really haven't talked about too much, but that's okay because that table is so easy, right? You're going to know exactly what to do here, right? So it's vapor pressure. What does that tell you? Vapor pressure tells you that if you're above this, you're a vapor. If you're below the curve, you're a liquid, right? So if you're above the curve, the graph, you're a vapor. If you're below, you're a liquid. Okay, so let's take a look. It says, identify the substance on table H with the weakest intermolecular force, right? What does that mean? If you have the weakest force between each other, holding them together, what does it tell you about the temperature at which you boil? You will probably boil earlier at the lowest temperatures. Even a slight change in temperature will cause you to break that weak link and then fly away as a vapor, right? So let's look at who we are. So at 40 degrees Celsius, what are we looking at? We're looking at 25, 30, 35, 40, 45, 50, right? So at 40, we are looking at right over here, right? So what do we know? At 40 degrees, right, who has the weakest? We're looking for somebody that's the most gaseous, right? That means, first of all, if you're not even sure, right? Let's take a look, right? That's water and that's ethanol. That's alcohol, guys, right? You already know from non-chemistry ideas that alcohol evaporates much easier than water. So what does it tell you? Who's the king here? The king here is this guy, propanol, right? Because it's the highest, right? So let the alcohol and water be your guide to figure out who is going to evaporate faster, right? Since we know that ethanol evaporates faster than water from just everyday knowledge, we know that an ethanol that's higher than water, that means the highest one probably has the easiest time evaporating. So the answer to that is propanone, right? Pro, up. Oh, what am I doing? It is propanone. Got it? All right, let's continue. Determine the vapor pressure of the ethanoic acid, right? See what I'm doing? I'm circling and highlighting. So if you don't have these marks that I'm making on your test booklet, you're taking the test wrong. So make sure you are underlining things. So determine the vapor pressure of ethanoic acid at standard pressure and 50 degrees Celsius. That's important, right? So remember, we're going back to table H. So let's go to table H, right? And let's go find ourselves 50 degrees. We are right here. Okay, and on top of that, we're looking at ethanoic acid. Ethanoic acid is this guy, which means we're looking at right here, right? That's 50 degrees at ethanoic acid. Let's see what we're talking about. They want the vapor pressure. So vapor pressure is over here. So what they're asking is, can we read this, right? At 50 degrees, ethanoic acid is like, it goes like here, right? So what is that? That's 10, 20, 30, 40, 50. So we know that's correct. So we know that this is what? This is 10. So that must be around 8, I think. So that's what we're going to put down, right? 8 kilopascals. All right, let's go to 62. 62 says, explain in terms of charge distribution why water is a polar molecule, right? What do we know about water? You guys remember we talked about water in class and we said that water has what? Negative oxygen end and then positive hydrogen end. And why is that? If you look at oxygen, right? Who's going to steal all the electrons here, right? All the electrons are going to hang out around the oxygen, right? You guys remember, right? The song I said in class, oxygen sings, my electronegativity brings all the electrons to my yard, right? It's better, right? It's better than yours. Remember that? All right. So if you really want the detailed explanation is what you look at electronegativity, right? Because electronegativity is what tells you how hard something pulls electrons, right? So if you look at electronegativity, which is right here, right? For oxygen, right? Electronegativity is 3.4. But what's hydrogen? It's 2.2, right? So obviously oxygen has a stronger electronegativity, right, than hydrogen, which means that electrons are going to be pulled towards oxygen, right? Right? Electrons are going to move towards there, which means it's going to be negative on this side. And then the hydrogens get left high and dry. So therefore, the hydrogen part is a slightly positive, right? So the other way to remember is, right, it looks like a Mickey Mouse, right? Just know that Mickey Mouse's ears are positive, while Mickey Mouse's face is more negative, right? All right. So why is water a polar molecule? Well, easy, right? We just said what? Oxygen has a larger electronegativity, right? Than hydrogen, which causes what? Electrons to be distributed how? You guys remember? How do you tell if a molecule is polar like water? Asymmetry, right? You remember? If it's asymmetrical, it's polar covalent, whereas if you see symmetry, it's non-polar covalent, right? All right, let's go. Number 63. You're thinking, oh no, Mr. Kim, it's organic, right? And again, at the time of this recording, we didn't cover organic yet. But I'm going to show you how easy it is, right? Even if we didn't cover this. It says, identify the class of organic compound to which A belongs. A is this one, and look at this. It looks like this, okay? What do you notice here? You notice here that you see an OH, right? Like this, right? So what we're going to do is we're going to go to the reference table and we're going to go to the list of organic chemicals right here, organol groups. All right. So what are we looking for? We're looking for something that has OH popping off all by itself with nothing else, right? And to do that, we go to the general formula, right? So what do we see? There it is. We see here that they all have R's, but this is the only one that has an OH coming off, kind of like this one, right? So what is that called? That's an alcohol. See that? The class of compound, right? So they said identify class. That's it, right? So you just write alcohol. It's that easy, folks. Let's go to 64. Draw the structural formula for dimethyl ether, the isomer of molecule A. Now, in class, I said long time ago that isomer is something that looks the same, right? Like isometric, right? Is a or isosceles triangle has two angles that are they're similar to each other or same with each other. So they want a formula for dimethyl ether, which is an isomer of molecule A. Well, here's how to do this. You look for dimethyl ether. We're looking for the ether, right? So let's go look for our ether. Oh, look at that. We have an ether right here. Okay. So how do you do ether, right? So ether means that there's an O in the middle, right? Ether means there's an O in the middle and there's a R. Now, if you look, it actually tells you somewhere here what R is, right? If you go, I think down here, it says R represent the bonded atom of groups of atoms. And specifically, it's carbons and hydrogens, okay? All right. So now that you know that, right? What else? We know that the formula for dimethyl ether, right, has to have an O in the middle with things on the side like that, right? So what are they? Well, it's dimethyl 2, and what's methyl? Let's go. If you go over here for the names, meth is 1 carbon, right? And there's 2 of them. So what do you think? What do you think? So if you go here, right? Methyl means 1 carbon, but there's 2 of them. Do you think it makes sense to maybe do that? Yeah, right? And then what else? You know that all the carbons has to have a bond, right? So in organic, any carbon that's sitting here, it has to be connected to a hydrogen like this, okay? Again, we'll cover that, okay? And could you put dots to show valence electrons, as in like the oxygen? Can you do this, right? Because you need to show octet. You could. However, this is not Lewis diagram. It's actually asking you what? It's asking you to draw a structural formula. So it doesn't actually have to show all the valence electrons, right? So you could put it down if you want to. But essentially, in the end, you want to draw an ether, which is an O in the middle with junk coming off either end. And you know, it's dimethyl means two meth or two single carbons. So it's going to be single carbon here, right? And we know that because it's single carbon, there are hydrogens coming off, right? Like this, okay? So I wouldn't expect you to be able to do this right now, but after we cover the organic, you should be able to do this with no problems. All right, let's continue. And some of you might actually understand what I'm trying to tell you right now. All right, so let's go. 65. Write a chemical name for the compound represented by molecule B. All right, so let's go see what that one looks like. All right, you got molecule B over here, right? So what do we see? We're looking for special things that give it away. And for me, what is it? It's this and this, or more specifically, that, right? That looks pretty special to me, right? So let's see if we can go find that. We're looking for a carbon. Oh, look, we already found it. Carbon, right? Right now, if you're thinking, oh, look, Mr. Kim, I see it right here. That's a hard no, right? Because why? Look at this. All three of these guys have a carbon, right? Or actually, four of these guys have a carbon with a double bond, like this, right? But notice what it's got. We got a hydroxide coming off on the right side. So let's go take a look, right? The only one that has hydroxide coming off right now, right, is this guy, isn't it? All right. So how do we name this? Let's take a look. Let the example be your guide, right? So let's go to look at our example, right? It's prop anoic acid, right? Let's take a look. What does prop mean? Prop is right here. Prop is 3. You see that? So if you see prop and that's 3, let's go back and look at our example one more time. How many carbons do you see? 1, 2, and 3 carbons. And that's why this one is called prop. So essentially what we do is that count the number of carbons, and then it's because of this, it's an anoic acid, right? So let's see if we can put that together in here, right? Let me get rid of some of this, right? And ask ourselves, okay, how many carbons we got? We got 1, oh, and a 2, right? Let's see if that matches up. That's right. We counting including the number of carbon that's attached to the double bond O. You see 3 for prop. Here we got 2. What is 2? Right? 2 is eth. Be careful, it's not di, right? Because we're not doing formula. It's not inorganic. This is organic, right? So it's eth, right? So therefore, that means because we see 2, it's going to be eth, and then we attach to it anoic acid, right? So the way we're going to call this is eth, because we see 2 carbons, and then it's anoic acid. Good. Let's move on. Go to 66. During a laboratory activity, first of all, this is the other thing I do, right? That I forgot to mention, 66 through 69, because I'm a bit of a scatterbrain. I actually do this, right? So then I know that that's actually part of the same group, right? Let's keep going. All right. So during laboratory activity, appropriate safety equipment was used and safety procedures are followed. Student investigated relative chemical activity of four metals, right? By placing one piece of each in an aqueous nitrate solutions of each of the four metals. The observation from investigation are shown below. Okay, let's keep going. The student wanted to use information from the investigation to make an operating voltaic cell using, oh, look, it's electrochemistry, right? So what do we know about this, right? It's our jam, right? It's my jam. Why do I write that? Because I'm psyched, because this is what I'm good at, or you're good at, right? Or we're good at. All right, it says identify the most active metal and the least active metal used in this investigation. If only there's a chart of active metals. Wait a minute, right? Some of you guys are screaming at me right now saying, oh, go to table J, go to table J. Let's go to table J. Oh, look at that. Activity series, right? So let's take a look, right? But you don't even have to look at this. Let's take a look and see what we got. All right. So you remember activity? It's the highest, that's the most active, and then the lowest is least active. And what do we know from class? You guys remember gold, silver, and copper is low, so that's out, right? Oh, actually, let's not do that because I need that, right? So I'm gonna put Cu, Mg, Zn, and Ag, right? So what are we looking for? We're looking for most active means what? Highest. And least active, lowest. So do you see what I did? I actually screwed up by crossing out copper. The lowest guy, I think, is going to be copper. You guys remember, copper, gold, and silver are all doing the bottom, right? And look at that, right? So that's the least active. So out of the group, right? Unless we have silver and gold. Oh, and look at this. We have silver, right? Which means that who's the lowest? Silver is the lowest, right? So therefore, the lowest is going to be that guy, right? It is the lowest, right? Who's the highest? Well, copper is actually a little bit higher, so I think copper is out. Magnesium, zinc are probably going to be higher, right? So let's take a look. We got magnesium here, and where's zinc? Zinc is right here. So who's the highest? Magnesium is, right? So highest is magnesium, lowest is silver, so that's what we're going to write. So most active metal is going to be magnesium, who's the highest, and least active metal is silver. That's going to be Ag. Okay, everybody, okay? Let's continue. Determine the oxidation state of nitrogen AgNO3 solution. My goodness, not only this is our gem, it's a gem within the gem, right? Because we're so good, right? Let's go look, right? How do we do this? Oxygen -2, right? How many we got? We got 3, so it's gonna give you a total of -6, right? And then let's go to silver. Oh no, I don't know what silver is. Well, don't worry, right? Because what do we do? If you don't know it, go look it up, right? Some of you might know it, right? And you're screaming, but silver is, it's only got 1, right? It's plus 1. All right, so we know that silver is +1. So we got a +1 -6. What do you think that is? That's right, it's +5. It's that easy, right? So you're just going to write +5 like that. Let's go to 68. Write a balanced half reaction equation for the oxidation of zinc during this investigation. Look, we don't need anything, right? Because remember what it said here? Your knowledge of chemistry. So you can do this, right? Oxidation of zinc is what? Rusting of zinc. So which means what? Solid is getting looser, right? It's disappearing. So you're starting with your solid zinc, and what else? It's oxidation, right? You remember Leo, which means electrons being lost, which means electrons on this side of the reaction. And then you're thinking, well, Mr. Kim, how do I know what this is? Well, like I said, go back, right? What's zinc? Zinc is +2. It's that easy, guys, right? +2. And how do you balance all this? You need 2 electrons. And we're done, right? So that's all we're going to write. We're going to put zinc solid oxidizing into zinc 2+. And what is that? You remember that's aqueous plus 2 electrons. So it turns out, do you need to write the states of matter, solids, and aqueous? You don't have to, right? It looks like in the answer key, they don't seem to really care. All right, let's keep going. Identify a metal in this investigation that could be used as the cathode in the other half cell in the student's voltaic cell. All right, let's see what the student is doing. All right, so the student wanted to use information this and to make it operate as voltaic cell using a zinc electrode. So it means that we got zinc on one side and we want on the other side, except what do we want? We want a cathode. Remember, what's that on an ox? It's a red cat. Hello. Red cat sat on an ox, right? So on a cathode, we're looking for reduction, right? So we want a metal to reduce here, right, on this side, which means if this is reducing, right, we want the zinc to what? To oxidize, right? So how do you get it to happen, right? You remember this chart that we have? Let's go. The chart, table J. Hello, table J. All right, remember, it's oxidation on top and reduction on the bottom, right? So what does that tell you? We want zinc to oxidize. So you want zinc to be higher, and you want your mystery metal to be lower in table J, right? So you want to pick a metal that's lower than zinc on table J. Is that making sense? All right, so let's take a look. You can't pick any metal though, right? Because we are limited to these guys. So you ask yourself, who is lower than zinc? That's copper, magnesium, or silver, right? So who is lower than zinc? Let's take a look, right? What question was this? This is 69. Hello, who's lower than zinc? Copper is, or silver, right? But let's see. Let's see what the question is actually asking you. Identify a metal in this that could be used as a cathode in the other half cell in the student's voltaic cell. Okay, so what happens if you use copper? If you use copper and zinc, then what's going on? Because you remember, student is stuck to using zinc. Zinc has to be one side. So if zinc is one side, right? Let's pick a different color so we can differentiate. Zinc is one side, and let's say if you chose copper, then what would happen? Zinc is higher, so it will oxidize, and copper will reduce. Is that what we're trying to get happening here? A metal that could be used as cathode? Well, yeah, because reduction is cathode, right? And you remember, red cat sat on an ox, so therefore this does work, right? So the answer is copper. Now, I'm not sure, but could you also use silver? What do you think? Could you use silver? Sure you can, right? Silver would work as well because silver is lower. What's one metal that wouldn't work? That's right, magnesium wouldn't work, right? Because magnesium is what? Higher than zinc, right? So you want to pick a metal. So I think that you can get away with number 69 by also putting down silver. Don't quote me on that though. Number 70, let's go. Number 70, student investigated the properties of solutions by dissolving, right? 46 grams of ammonium chloride in 200 grams of water at 20 degrees Celsius. Now, again, don't just go NH4Cl. As you're taking these practice, you should practice naming these. Do you see what I did? I didn't say NH4Cl. I actually named it. And if you have a hard time naming this, take the time to go figure out what the name is. Because if you keep doing it, you'll get better at it, right? Because some of these, they're going to ask you to name these, right? So dissolving 46.0 grams of ammonium chloride in 200 grams of water at 20 degrees Celsius. The gram formula mass ammonium chloride is 53.5 grams per mole. Temperature of the solution decreases as ammonium chloride is dissolved during the laboratory activity. Appropriate, whatever. State in terms of temperature why dissolving of the NH4Cl is classified as an endothermic process. All right, so what do we know? Exothermic means what, kids? Right, releasing energy, right? So endothermic process means what? It's absorbing energy, right? If something absorbs energy from you, how does that feel? It feels cold. All right? Because temperature went down. Is that what happened? Let's see. The temperature of the solution. Oh, look at that. Decreased. Right? Isn't that a definition of endothermic reaction? So it says state in terms of temperature, right? But they literally gave it away. They said you have to talk about temperature, right? So be careful. When it says terms of temperature, you have to use those words, right? So you would say what? The temperature, what happened? Decreased. That's it. You don't have to write too much, right? All right. Classify in terms of saturation, the type of solution produced in this investigation. Do you see where we're supposed to go now? Saturation curve, right? Where am I going, guys? I'm going up, wrong direction. That's where I'm going, right? Going over here, right? Hey, look at that. Do we see ammonium chloride? Yes, we do. It's right there, right? So you see ammonium chloride. Good. Now what? It says, right? 46 grams of ammonium chloride and 200 grams of water. Hey, what happened? You remember? This is the thing I told you to be careful about because why? It is per 100 grams of water. So you got to do that mental math of either taking a half or doubling it, right? We'll figure that out later, right? So what do we know? We put dissolve this much, okay? Everybody okay? We dissolve that much. Let's take a look, right? So let's figure out what's going on. Ammonium chloride is this curve right here, right? And what's the temperature? Temperature was at 20 degrees Celsius. So at 20 degrees Celsius, that curve, it meets right over here where I put the blue dot. All right. What does it tell you? This is approximately what? This is approximately 38 grams. But remember, that's 30 grams in 100 grams of water, right? So what do you think? 200 grams of water would take how much? More or less? What do you think? It'll take more. How much more? Twice as more, right? So it's twice 38. That's going to be what? 8 times 2 is 16, plus 60. That's 76, right? So this means that it's going to take 2 times 38 or 76 grams in 200 grams of H2O, right? What does that mean? That means it'll be at the line. You guys remember what the line meant? Line meant, what does that mean? Right? That's right. That's saturated, right? So you need 76 grams in order to become saturated. But how much are we dissolving? You're only dissolving 46. So what kind of solution we got? What do you think? We got unsaturated, right? Unsaturated solution. All right. Raise your hands if you have questions. I'm kidding. I'm kidding, right? Okay. Number 72. Based on table G, identify the solute that has a solubility at 20 degrees Celsius that is closest to the solubility at 20 degrees Celsius. Guys, I already figured it out. At 20 degrees Celsius, ammonium chloride is this. Hey, what else? See this line? Who's that? That's sodium chloride. They're both at the same exact line point, right? So therefore, the answer is sodium chloride, right? All right, let's keep going. Determine the number of moles of ammonium chloride dissolved in 200 grams of water in this investigation. All right, so be careful. This is extra information, extraneous information. How much did we dissolve? We dissolved 46 grams of NH4Cl, right? Was dissolved. All right, so how do we get to moles of NH4Cl? How do we do that, kids? right? You need a formula of mass, right? But before you go running over to look for it, guess what? Guess what? Right? Do I have a highlighter here at all? I think I can make one. Highlighter? No, that's gonna, oh, no, I do have one. Yay. Look at that. I've never used it, but let's go. Look at this. The grand formula mass is given to us. That's terrible highlighter. Right? Do you see that? All right, it's given to us. All right. So what do we know? It's 53.5 grams per mole. Look at that. You don't even have to go look it up, right? You don't have to go calculate it. They gave it to us. How easy is that? So when you have that, what do we get? We get 0.85981, except how many stick figs are we using, man? We got 200, no, that's not it. Number of moles is what? You got to go 3 sig figs right over here, and then 2 sig figs here. So your answer has to be what? Within 2 sig figs, right? Because this is 2 sig figs, right? So it's going to be 0.8, and then you got to stop here. So it's going to be 6, right? So let's go and put that down. 0.86 moles. All right, let's continue. Ooh, look at that, ppm, right? You know there's an equation for that, right? All right. Process of evaporation affects the concentration of ions in a sample of seawater. The table below shows the name and concentration of different ions in seawater sample. Concentration expressed in grams per 1,000 grams of seawater. All right, let's take a look. Determine the concentration of potassium ions, that's this guy, in parts per million in the sample of seawater. All right, so what do? We got to go get the equation, right? Let's go figure it out. I know some of you guys know it because I said it doesn't hurt to memorize it, but it's over here. Parts per million. Hey, there it is. It's that, right? So it's mass of solute over mass of solution, right? So let's go take a look, right? So mass of solute would be this, right? Over mass of solution. Look, they already gave it to you, right? So this is actually quite straightforward, right? Mass of the solute over seawater, that's the solution, right? Except what else? And then you got to multiply by 1,000,000, right? And before you grab that calculator, stop for a second and let's take a look at this, right? You got 1,000 on the bottom here, right? 3 zeros. What happens? Isn't that what happens? And if that's what happens, what's multiplication by 1,000? You move the decimal places 3 to the right, which means it's 394, right? It's 394. And what else? You go over here and you write 394 parts per million, and we're done, right? Let's go to 75. State what happens to the potential energy of water molecules as they evaporate from sample of seawater, right? Okay, we're evaporating and we're talking about potential energy, right? What's the only graph that you know of that shows that? Can you guess? Right, it's the one with the 2 plateaus and 3 slopes, right? All right, now let's take a look, right? You remember it's solid, liquid, and gas or vapor over here. All right, so changes as some of the water evaporates from water. So you're starting as water right here and evaporate. So what are we doing? We're going this way right here. Anybody remember what changes in the plateaus? Because the only way for you to know is to memorize it. This is potential energy, right? Right? So, oh, I'm sorry. I circled the wrong thing, but it doesn't matter. It's the same exact thing we're looking at, right? So it says potential energy, PE, right, as they evaporate from sample of seawater. So again, we're starting with water and evaporating, right? So what do we know? Potential energy goes up, right? So we're going to go to the problem and say the potential energy goes up or increases, right? Like that. Okay, let's keep going. All right, state the concentration of the ions in a sample of water change as some of the water evaporates. Hey, what happens when water evaporates from seawater? Does it get more dilute or saltier? Right, it's saltier. If it's saltier, what does it tell you about the concentration of salt? Right? It increases, right? So you would say the concentration would increase. Okay? It's that easy, guys. Let's go to 77. Use the key in your answer booklet. Draw at least 2 water molecules in the box showing the orientation of each water molecule towards the bromide ion. All right, let's go. All right, bromide. What do we have to notice here? We got to draw a water molecule like this, right? But do you guys remember what I said about Mickey Mouse? Which side is more positive? The 2 hydrogens, right? Or the ears are the positive side. And then the face or the chin is the negative side, right? So let's go to the bromine right here. Which side of the Mickey do you think is facing towards the bromine, right? What do you think? That's right, the ears, right? So I'm going to say, draw a water molecule. It doesn't matter which direction you draw it from. They said at least how many though? 2. So you got to draw 2. Could you draw more? Yes. Can you draw like 10? Yeah, but now you're just being a jerk, right? That's it. That's the minimum that you need to do, right? So that's correct. All right, let's keep going. During a laboratory activity, appropriate safety equipment was used and safety procedures are followed. Student performed 3 trials of a titration. Oh, what's that? Acid base, right? Right? What's this? That's my jam, right? Again, we're super excited about this because we know how to do this, right? Using 0.16 molar KOH, right? Mental note, that's what? That's right, it's a base. To determine the unknown concentration of a solution of hydrochloric acid, which we know is to be an acid, right? They told you that, duh, right? The volume of the solutions are shown in the table below. It says identify the positive ion in a solution of hydrochloric acid, right? Is it me or am I doing a deja vu? Because didn't they ask the exact same question in the other free response? So what is it? The positive ion, right? What's the answer, kids? What was that? 78 would be H plus, right? I think this was literally the same question they asked in the other test. 79. Complete the equation in your answer booklet for the reaction that occurs during this titration by writing a formula for each product, right? Hey, let's take a look. Hey, what do we know? Right? What does this look like? Acid plus base gives you what and a what? Water is one of them, right? And gives you the salt. And then you remember what we said? Titration is what? Or neutralization is a subset of? And I see the hand shoot up, right? Double replacement, right? So where'd the water come from? Water came from these 2, right? Which means we're going to put these 2 together for the salt, right? And yeah, could you put ClK? Yeah, but you know what? You're better than that, right? What goes first? The cation and an anion. Just be careful though, right? Potassium is +1, chloride is -1, so therefore crisscross drop charges, it should be KCl. Don't forget that, right? Don't forget to do crisscross drop charges, right? So this would be the actual equation that we have, right? So that's the answer. It's that easy. Okay, let's keep going. Show a numerical setup for calculating the molarity. So again, do they want the answer? Did they say they want the answer? No, they want the calculation. They want the molarity of the HCl solution using the titration data from trial 2. That's important. Let's go to trial 2. What do we got? We got volume of HCl. What's this? Volume. V. And who's that? That's acid. VA is that. And what's this? This is VB, right? Like that. So what else we need? We need the Ma and Mub, right? What do we got? What's this up here? That's MB, right? That's base, right? And then what did it say? Molarity of hey, that's MA, right? So that's our unknown, right? So let's go. Let's go set this up, right? So I'm gonna go here, set it up. So we got Mava and Mub Vub, right? And then I think MA is our unknown. All right, so let's go. VA is our 10.0 milliliters. MB is up here, 0.16 molar, and then VB is 15. Right? We all good? So now what do? We plug it into our equation, right? So plugging into our equation, we get one of these jobs, right? We get, what do we get? MA MAVA equals MAVUB. And we're solving for MA, so that's why we're going to divide both sides by VA, like that, right? Now what? Let's plug in. You got 0.16 molar times VB is 15.0 milliliters. If you're screaming, Mr. Kim, you didn't convert it to liters. Kids, you don't have to. I'm gonna show you in a second why. Why? Kids, what happens to the milliliters? That's right, it cancels itself out and leaving us with molar, right? So therefore, we're okay. We don't have to. What happens if you do that? What happens if you change the VA to 0.01 liters and then VB to 0.015 liters? It's going to be the correct answer. They're going to still accept it, okay? But what I am going to do is, because this is the answer, I'm not going to cross it out, right? 15.0 milliliters, right? So guess what? You're done. Don't touch that calculator. We're done. And please make sure you circle your intended correct answer, okay? All right, let's keep going. Number 81. Explain in terms of experimental design why it's better to use data from multiple trials of titration to determine molarity. More data, right? Where's that from? Dude, guys, that's from first day of classes, right? What do we know? More data, more what? More precision, right? Right? So, and accuracy, right? But you could actually, so the answer is, right? More data will produce more accuracy, right? In the experiment. We all good? Yes. All right, let's keep going. That's 81. 81's done. Let's go to 82. Oh, it's nuclear, right? And you're thinking, oh man, nuclear. Like I said, by this time, we haven't covered nuclear yet. That's next week, but I hope by this time you know how to answer like half of these already, right? So let's look at number 82. State the neutron to proton ratio in helium 4:2, right? Guys, it's an isotope, right? Look, it's 4:2 helium, right? Anybody want to take a guess how many proton helium has? And if you don't know, shame on you, because why? Where do you go? You go over here, right? Hello. You go here and you go look at helium. What do we know about helium? Helium has how many protons, kids? It has 2 protons. All right. So it has 2 protons, but its molar atomic mass number is 4. What's that? That's proton plus neutron, right? So anybody want to take a guess how many neutrons there are? If you have 2 protons, but protons plus neutron is 4? That's right. It's 2:2, right? So what's the ratio? It's 2:2, right? So we're going to write, right, 2:2, right? In other ways, you can write this as what? You can write 2:2, or you can simplify and say it's 1:1, right? All 3 of these correct answers, okay? Let's go. 83. Based on table N, state the decay mode of tritium. What's tritium? You guys remember? It's right here. Tritium is this, right? So state table N. Let's go. Let's go to table N and see if you really need to spend a week on this. Table N, selected isotopes, right? We're looking for tritium, right? Holler if you see it. Holler if you see it. Guys, you didn't say anything. It's right here. guys? Tritium, right? So what? Oh, Mr. Kim, there's no 1. It's because it's 1 understood, remember? All right, so let's go. Oh, I just lost my screen. Oh, there it is. All right, ready? This is how easy it is, guys. Decay mode. What is it? It's beta minus, right? It's beta minus. So what is it? Beta minus. Just give me, what if I don't know how to draw that symbol? I don't know, write beta, right? You can do that, but it doesn't matter. 84, let's go, right? Determine the time required for a 1 gram sample of the tritium produced to decay until 0.25 is unchanged. You guys remember what we said? We said you're eating half and leaving behind half, right? Remember we talked about Justin eating his pizza? So let's imagine, right? If you start with 1.00, after 1 half-life, right? What do we end up with? Right? How much of 1 do we end up with? You end up with 0.5. What happens if you go through another half-life? Then we're cutting that into another half, right? That's right. You would end up with 0.025. So it tells you how many cuts did we make? We made, right? How many cuts or half-lives we make? We made 2 half cuts, right? So the question is, how long does it take to make those cuts, right? Well, it's right in the thing, right? If you go here, half-life for tritium is 12.37 years, which means this took 12.37 years, and that took another 12.37 years, which means what's the math? It's 2 times 12.37. That's it, right? That's literally what it is. And if you do that, what do you end up with your answer? It's 12.37, so it's going to be 24.62, I think, right? I don't know if my mental math is correct. All right. All right. I don't even have to go to 85 to actually answer this. I know what they're going to say. They're going to say to complete it, right? Oh, look at that. Complete the nuclear equation in your answer booklet, blah, blah, blah. I'm not even going to look at it. So if you remember what we did in the other one, let's take a look, right? How do you do this, right? On either side of this arrow, the numbers on the top and bottom has to equal each other. So let's look at on the right side. It's 3 and a 4. So the total on the top has to be 7. Total on the bottom has to be 3. Do you see that? Do you see that? 3 plus 4 gives you 7. 1 plus 2 gives you 3. Let's go to the left side. Left side already has a 1 on the top, which means what's the mystery number? What plus 1 gives us 7? 6 does. What up at the bottom? It's a 0, right? Which means what plus 0 gives you a 3? That's a 3, right? Now what do we do, right? How do we go find out who this person is? If you don't remember, just go look up helium in the periodic table, and you notice helium's atomic number is 2, right? So therefore, we're looking for a guy whose atomic number is 3, right? Do you know top of your head? I don't. Actually, I do, but I'm going to pretend I don't, right? It's what? It's already circled. It's 3, right? So it's lithium, right? And we're done. It's that easy. And guess what, kids? That's it. We're at the end of this, right? We're done, right? And it's this easy. So, obviously, would you find this easy? You shouldn't. However, as you do multiples of this, and if you get stuff wrong, and then you hear my explanation, you're going to have to look at that, pause, go read it in the textbook, go look in the review book, study some more, and then take the next FRQ and see how well you do. Okay? All right. So I hope this was helpful. I'll see you next time.